Welcome to the DIY Honda Garage channel. The DTC P16E3 indicates a communication error related to the PGM-FI, Programmed Fuel Injection System's battery sensor via the LIN, Local Interconnect Network. This error specifically denotes a failure in communication between the battery sensor and the vehicle's onboard computer systems. The 12-volt battery sensor monitors the battery state and relays pertinent data to the Engine Control Module, ECM, through the LIN protocol, which is a low-cost, serial communication method designed for automotive networks. When this communication is interrupted or fails, it can lead to performance issues or failures within the fuel injection system. Effective troubleshooting is crucial to pinpoint the exact cause of the error. The initial verification process will help establish whether the issue is confirmed or intermittent, thereby guiding the next steps in diagnosing this error. The 12-volt battery sensor is pivotal in providing real-time information about the battery's condition, such as voltage and charge status, which helps the Engine Control Module, ECM, optimize engine performance. This sensor communicates via the LIN, Local Interconnect Network protocol. Typically, you will find the 12-volt battery sensor located near the battery connection points under the vehicle's hood. The LIN network links various components by allowing them to communicate with minimal wiring. The ECM processes the data received from the battery sensor to adjust fuel injection accordingly, which is critical for maintaining vehicle performance and efficiency. A breakdown in this communication can result in various operational issues, making the understanding of this error essential for effective troubleshooting. Several factors can lead to the P16E3 error. 1. Loose battery terminals can disrupt power supply or communication channels to the battery sensor, causing the error. 2. A faulty battery sensor may not transmit accurate information to the ECM, leading to misdiagnosis. 3. Wiring issues, such as shorts or opens in the LIN communication line, can prevent successful data transfer between the sensor and ECM. 4. Problems with the PCM, Powertrain Control Module, itself can affect its ability to interpret data from the battery sensor. Each of these potential issues should be meticulously explored during the troubleshooting process to accurately identify and rectify the source of the DTC P16E3. When DTC P16E3 is present, various symptoms may manifest. A warning light on the dashboard could alert the driver of an underlying issue. Engine performance may become erratic, as the ECM relies on consistent information from the battery sensor to make real-time adjustments. Additionally, if the battery sensor provides inconsistent or unreliable data, this could compromise system functionality. Furthermore, poor fuel economy might result due to the ECM's inability to optimize fuel injection settings properly. As these symptoms often overlap with multiple issues, it's crucial to confirm that DTC P16E3 is indeed the root cause before proceeding with repairs. The first troubleshooting step involves verifying the problem before proceeding with detailed diagnostics. Start by turning the vehicle's ignition to the on mode, which activates the electrical systems, allowing for communication checks. Use the HDS Honda Diagnostics system to clear any existing DTCs. This step is crucial as it resets the system and prepares it for a new diagnostic read. Next, switch the vehicle off completely and wait for 60 seconds before turning the ignition back on. This waiting period allows the system to fully reset and helps in capturing accurate data during the subsequent DTC checks. This check will determine if DTC P16E3 is still present or if it is resolved, leading the technician to the next steps in the repair process. In this step, you will conduct a check for pending or confirmed DTCs using the HDS. This involves assessing whether DTC P16E3 is also indicated, as this could signify additional systemic issues. If P16E3 is confirmed, you will follow the troubleshooting process for that code, leading you to step 4. If P16E3 is not found, continue to step 3 for further diagnostic actions. The significance of this check lies in its ability to streamline the troubleshooting process, ensuring that related DTCs are examined concurrently to identify if they share a common problem. Through this systematic approach, the technician can isolate the issue more effectively. In this third troubleshooting step, utilize the HDS to check for pending or confirmed DTCs again. This time, the focus shifts to the P16E3 code, which indicates a shutter grille LIN communication error. If this DTC is confirmed, you will redirect your troubleshooting to step 8, dedicated to that error. Conversely, if there is no indication of P16E3, continue on to step 12. This step is vital for discarding additional error codes that may complicate the troubleshooting process. A thorough examination of all relevant DTCs allows for better isolation of the P16E3 issue and potentially points to interconnected failures within the system. This fourth step focuses on determining the potential fault area related to the battery sensor or LIN line. Start by turning the vehicle to the off or lock mode, which ensures that all electrical connections are inactive and safe for handling. Disconnect the 12-volt battery sensor 2P connector, which is crucial for facilitating continuity testing. With the connector disconnected, check for continuity between test points 1 and 2 as outlined in the diagnostic guide. Test point 1 is the female terminal number 2 of the 12-volt battery sensor connector, while test point 2 is body ground. If continuity is observed, it indicates that the LIN wire is intact and leads to subsequent checks in step 5. Conversely, a lack of continuity points to a problem in the circuit that requires further investigation in step 6. In this fifth troubleshooting step, the focus shifts to checking the LIN wire for shorted connections. Begin by jumping the SCS, System Control Short, line using the HDS, and wait for more than 1 minute to stabilize the communication. Afterward, you will check for continuity between the 12-volt battery sensor 2P terminal number 2 and body ground. This is while disconnecting connectors one at a time from the alternator, PCM, and both upper and lower shutter grille 4P connectors. The goal is to observe if continuity ceases when one of these connectors is removed, which would indicate that the corresponding connector is causing a short. If you discover that continuity is lost upon disconnecting a certain connector, the LIN wire can be considered functional, and it's time to replace the component that caused the issue. In this step, you will determine if the 12-volt battery sensor is faulty. Reconnect the 12-volt battery sensor 2P connector to resume its normal function. Following this, disconnect the alternator 1P connector to isolate its impact on the system. Now, check for continuity between the alternator 1P connector terminal number 1 and body ground, while ensuring the vehicle is in the off or lock mode. If continuity is present, it indicates that the sensor is likely faulty, and you will need to replace the 12-volt battery sensor. If continuity does not exist, proceed to step 7 for further troubleshooting actions to determine whether additional repairs are necessary. For this 7th step, you're looking for an open in the LIN wire related to the battery sensor. Begin by jumping the SCS line with the HDS once again and waiting more than a minute to stabilize communication. Following this, disconnect the 12-volt battery sensor 2P connector along with the PCM connector B51P to set up for continuity testing. With these connectors removed, check between the 12-volt battery sensor terminal number 2 and the PCM connector B terminal number 40 for continuity, while the vehicle is in off or lock mode. Presence of continuity implies the LIN wire is intact and functioning correctly. If there is no continuity, you will need to repair the open wire between the PCM and the 12-volt battery sensor, which is crucial in restoring proper communication within the system. In this 8th step, you'll repeat a previous process to ascertain the condition of the LIN wire connected to the battery sensor. Again, ensure the vehicle is turned off and disconnect the 12-volt battery sensor 2P connector. Make sure to check the continuity between test points 1 and 2, where test point 2 remains body ground and test point 1 is the sensor's female terminal number 2. If continuity is present, it indicates the wiring is intact, allowing you to proceed to step 9 for further checks. On the contrary, if continuity is absent, this suggests that there is a break in the wiring, which will necessitate additional investigation outlined in step 10. In this 9th step, continue to check for shorted connections in the LIN wire. Similar to earlier procedures, jump the SCS line with the HDS and wait for over a minute. During this time, continuously check for continuity between the 12-volt battery sensor terminal number 2 and body ground. Disconnect connectors one at a time from the PCM, alternator, and both upper and lower shutter grille connectors to see if this impacts continuity. If the continuity is interrupted upon disconnecting a specific connector, it suggests that the LIN wire is functional, and you should replace the component that caused the fault. If there is no change in continuity, regardless of which connector is removed, it indicates a short which requires repair. In this 10th troubleshooting step, establish the solder connection integrity involving the 12-volt battery sensor and shutter grille connections. Reconnect the 12-volt battery sensor 2P connector to restore sensor functionality. Next, disconnect the upper and lower shutter grille 4P connectors to further assess potential issues in the circuit. You will then check for continuity between the shutter grille female terminal number 3 and body ground. The vehicle should be in the off or lock mode during these checks. If continuity exists, it confirms that the LIN wire is functioning well and indicates that the battery sensor may need replacement. If continuity does not exist, proceed to step 11 for additional diagnostics. Continuing with this 11th step, you will verify for a potential open connection in the LIN wire. Jump the SCS line using the HDS again, allowing for stabilization of communication. Subsequently, disconnect the 12-volt battery sensor 2P connector, along with the PCM connector B, 51P. Test continuity between the 12-volt battery sensor terminal number 2 and the PCM connector B, terminal number 2, 40, while ensuring the vehicle remains in the off or lock mode. If continuity is confirmed, the LIN wire is functioning without fault, enabling you to check for other documentation related to DTCs or substitute a known good PCM. However, the absence of continuity will necessitate repairs to the open in the LIN wire between the PCM and the 12-volt battery sensor. In this 12th step, it's essential to check the integrity of fuse A24, located in the underhood fuse or relay box. Start by turning the vehicle off or lock to ensure safety while handling the electrical system. Inspect the A24 fuse, which is rated at 10 amps, for any visible signs of damage or failure. If the fuse is intact, you will proceed to step 13 for further checks. However, if you find the fuse blown, significant troubleshooting is needed to repair any shorts in the +B horn wire that connects the 12-volt battery sensor to the A24 fuse. Identifying and resolving any issues at this fuse connection point is vital for restoring the power and communication needed for vehicle performance. In this 13th troubleshooting step, You will measure voltage to further assess the battery sensor communication condition. Disconnect the 12-volt battery sensor 2P connector to prepare for voltage testing. Measure the voltage between the sensor's female terminal number 1 and body ground while the vehicle is off or lock. If battery voltage is present, proceed to step 14 for additional continuity checks. Conversely, if you do not detect battery voltage, this indicates an open circuit condition in the +B horn wire connecting the sensor to fuse A24. Repairing any issues in this area is crucial to restoring functional communication with the battery sensor and ensuring reliability of the fueling system. In the 14th and final step, you are set to confirm the integrity of the LIN wire once again. Begin by repeating the process of jumping the SCS line with the HDS to stabilize the communication mode. Then, disconnect the PCM connector B51P to isolate it from the circuit. Check continuity between the 12-volt battery sensor terminal number 2 and the PCM terminal number 40, while ensuring that the vehicle remains off or lock. If continuity exists, it indicates that the LIN wire is functional, and the issue lies with the battery sensor, which now requires replacement. Should the test reveal no continuity, repair any existing opens in the LIN wire linking the PCM and the battery sensor to restore proper communication throughout the system. After completing all diagnostic and repair steps for DTC P16E3, a final verification process is essential. Take the vehicle for a test drive after all repairs have been conducted to ensure that everything functions as intended. During this process, monitor the vehicle for any signs of erratic behavior or the reappearance of warning lights. Before concluding the repair, conduct another scan for DTCs using the HDS to ensure that DTC P16E3 and any other related codes no longer appear. Confirming system performance and ensuring smooth operation reaffirms the success of the repair, providing peace of mind for both the technician and vehicle owner alike. To minimize the risk of future occurrences of DTC P16E3, implementing a preventive maintenance routine is crucial. Regular inspections of the battery and its sensor connections can detect looseness or corrosion before they escalate into major issues. Consistently monitor the condition of the battery itself, ensuring it maintains its charge and integrity over time. Consider conducting periodic system checks with the HDS to identify any developing DTCs before they become problematic. Lastly, maintain cleanliness in the engine compartment, especially around electrical components, to prevent possible shorts or failures due to contaminants. All these preventive measures help ensure the long-term reliability and performance of the PGM-FI system in your Honda CRV. In conclusion, effectively addressing DTC P16E3 requires a detailed understanding of the PGM-FI-Battery sensor as well as the LIN communication system. Key components involved include the 12-volt battery sensor itself, the PCM, and various connections that must be systematically examined. Each troubleshooting step is vital in isolating the root cause of the communication error, enabling accurate repairs. The importance of proper diagnosis cannot be overstated, as it not only rectifies immediate issues, but also helps identify underlying problems that may affect vehicle performance in the long run. By following a methodical troubleshooting process and performing regular maintenance, you can ensure that the Honda CRV operates at peak efficiency while minimizing the risk of future faults. Please like and subscribe to the channel. See you next time.